Welcome students for today's lecture, and today's topic is resistance in series and parallel and some of the numerical problems based on the concept series and parallel. Okay, so in our yesterday's lecture, so we saw what is DC circuit and what is AC circuit and the relationship between the voltage and current for R load, L load and C load. So these are the things we covered in yesterday's lecture. But if you take any DC circuit or any AC circuit, this can be again divided into DC series circuit or DC parallel circuit or AC series or AC parallel based on the connection that was made between the components. For example, here we are going to concentrate only on resistance. So if you connect two or more resistance in series, then we can say the circuit as a DC series circuit. Or simply, if you connect two or three resistance in parallel, we will say that as a parallel circuit, DC parallel or AC parallel circuit, or it can be mixture of both series and parallel. So three resistance in series and again two resistance in parallel with a combination of both series and parallel. So these are the things available. Okay, so now in this video we are going to concentrate only on series and parallel for R alone, that is resistor alone. Okay, so what is series? What is parallel? So first we will see that. Okay, so two or more elements can be connected in series or said to be connected in series. So if they share a single node exclusively and it should carry the same current. Okay, so that is the definition for series connection. That is, every element should share a single node exclusively, that is unique node for that two element, and it should follow or the same current should flow through the elements. So that is the one point. So we will go for a simple definition. So just wait. And in case of parallel connection, so two or more elements are said to be connected in parallel connection if they are connected to same two nodes. That is the starting node and ending node. That should be same for all the elements that is connected, and they should have a same voltage across them. Okay, that is called as parallel connection. So let us take an example. So instead of going with this definition, you can simply say, okay, so this is a series connection. Okay, here the end terminal of this lamp is connected to the starting terminal of this lamp. So we can simply say, if two elements, okay, one end terminal of one element is connected to the starting terminal of another element without any interruption of any other element. So because here there is no connection, no any other connection. Okay, so then we can simply say these elements are connected in series and it should have the same current, because the current I is flow here means, so the same current I is flow through this lamp also. For series connection, the current should be same for all elements, not the value. Okay, the current, which current is flowing, that's the matter. And in case of parallel, so this is a parallel connection. Here you can simply say, so the starting terminal and the ending terminal, so both are same for both elements, both lamp. Okay, here this is the starting node and this is the ending node. So it is same for this lamp and this lamp. Whenever the starting node and ending node is same and the voltage, so if you see the voltage drop across this lamp, it should be equal to the voltage drop across this lamp. So then it should be considered as a parallel connection. So let us say here also. So here you can simply say, so these three batteries are connected in series. So that is positive terminal is connected to negative terminal, similarly positive to negative, and again positive to here, that is main supply voltage. Okay, so here based on this connection we can simply say these batteries are connected in series. And similarly, if there is a current flow, okay, then it will flow through the 12 volt battery and again it will comes to this 12 volt and again to that battery and it goes here. Okay, so the same current will flow from this terminal to this terminal. So this will be called as series connection. And here if you take the three batteries, if I connect all the negative terminal, okay, and all the positive terminal like this, then it is said to be parallel connection. Simply you can see here, so here the voltage is 12 volt and here also 12 and here also 12, and if you take a voltmeter and connect it here, it will show the same voltage, that is 12 volt. Okay, so this is a series connection of 4 resistors. So end terminal of R1 is connected to the beginning of R2. Similarly, end of R2 is connected to beginning of R3. Similarly for R4. So this is considered as series connection. And if a current I is flow here means, so the same current will flow here. Okay, so because if here value of current 5 ampere flow means here also the same 5 ampere will flow. There won't be any decrease in current after the resistance. So because of the current, there will be some voltage drop in this resistance, but current value won't change. So it will be same for all the 4 resistors. So this is for series connection. And in terms of parallel connection, okay. So the starting point of all the resistors R1, R2, R3, 4 is connected to this node. That is this short circuit, right? So a single node in the upper terminal and similarly a single node in the lower terminal. So the ending point also common. So if you take a voltmeter and connect it across these 2 points, it will be same for R1, R2, R3 and R4. But the current will be different for each resistor based on the value of resistance. Okay. So if you take the takeaway is nothing but if series, the current will be same. The voltage across each resistor is different. If you take parallel, voltage across the resistance will be same, but current through the resistance will vary based on the resistance. Okay, so let us see resistors in series. Okay, so consider a circuit here. Okay, here you have a DC voltage V and we have 2 resistors connected in series R1 and R2. Okay, the voltage drop across R1 is taken as V1 and voltage drop across R2 is taken as V2. The overall current through the circuit is I. Okay, the same current I is flow through R1 and R2. Okay, so as per Ohm's law, we can derive the formula for V1, that is voltage across resistor 1. So V is equal to IR. So here the current I is small I and resistor value is R1. So V1 is equal to I1 R2. Similarly, V2 is equal to I into R2. So V1 equal to I R1, V2 is equal to I R2. So this is the voltage across V1 and V2. Now here we can apply Kirchhoff's voltage law because it is a closed loop, right? And we have voltage sources V, V1 and V2. As per Kirchhoff's voltage law, the sum of all voltages in a closed path will be equal to 0. Then here if I take a leaving terminal, so that is plus V minus V1 minus V2 is equal to 0, which will be equal to V is equal to V1 plus V2, because if you take the negative V towards this side, so V is equal to V1 plus V2, but you know the value of V1 and V2. Okay, just substitute the value of V1 and V2 in this equation. So now we will get V is equal to V1 plus V2, that is I into R1 plus I into R2. So taking I as common, so I into R1 plus R2. So now we just compare this equation with Ohm's law. So V is equal to I into R. So where R is nothing but the resistance. So here in the circuit the total resistance R is equal to the sum of R1 and R2. Okay. So which is written as R equivalent. So here R equivalent is nothing but R1 plus R2. So if you connect any number of resistors in series, then the equivalent resistance will be equal to the sum of the resistance. Okay, so these two resistance can be replaced by a single resistance with the value of R equivalent. For example, if this is a 1K and this is a 1K, that is 1 kilo ohm, 1 kilo ohm, then the value of R equivalent will be 2 kilo ohm. Okay, so R equivalent is nothing but R1 plus R2. Similarly, if you take n number of resistors, okay, instead of 2, just n number of resistors, that is 1, 2, 3 to n, okay, then the sum of the resistance will give the R equivalent, that is R1 plus R2 towards Rn. So which is nothing but summation of your R, that small n is equal to the number of resistors. Okay. So similarly, already is right, V is equal to V1 plus V2, which is nothing but I into R1 plus R2. We know the value of I. So I is nothing but V by R. R is equal to R equivalent. So instead of I, so we can just substitute V by R1 plus R2. So combining these two equations, that is V equal to V1 plus V2 equal to I R1 plus R2, and the equation I is equal to V by R1 plus R2. So we can derive an equation for V1 and V2. Okay, so V1 is nothing but I into R1. Okay, so instead of I have just substituted V divided by R1 plus R2. Okay, similarly For V2, small I into R2. For small I have substituted V R1 plus R2. Okay. So here R1 plus R2 is nothing but your equivalent resistance. So this will be useful for a topic called voltage division rule, which will be learned in our second unit. But just to consider, if we want to measure the voltage across R1, this will be the formula. So where R1 is the resistor and V by R1 plus R2 is the current through the resistor. Okay. So just an example, find the R equivalent and total current I in the given circuit. Okay. So this is a circuit. Here we have a voltage source 9 volt and 6 resistors are connected in series. Okay. So they have asked for R equivalent. So just now we learned, right. So for n number of resistors connected in series, just sum of the resistors value. Then R equivalent will be equal to sum of all resistors, that is 330 plus 120 plus 1500 plus 47 plus 390 plus 180. So which will be equal to 2567 ohm. So this is the value of R equivalent. I am just adding all the resistor value. Now they asked for the total current I. So total current I is nothing but the current through the resistor, current through the circuit. Okay. So as per Ohm's law, I is equal to V by R. Here V they have given us 9 volt and R we just found out as 2567. So as per Ohm's law, I is equal to V by R equivalent. So 9 by 2567, which is equal to 0.0035 ampere. Or simply you can convert that to a milliampere, that is 3.5 milliampere. So instead of 0.005, you can simply put 3.5 into 10 power minus 3, that is equal to 3.5 milliampere. So next sum, using Ohm's law, calculate the equivalent resistance, series current and voltage drop and power across each resistor. So somewhat a bigger sum compared to last one. Okay. So here we need to find what is R equivalent, that's the one thing, and series current, that is what is the value of I. So next thing, and what is the voltage drop across each resistor, that is here what is V1, what is V2, what is V3, and third one, last one, power across each resistor, that is what is P1, P2 and P3. Okay. So I'm not gonna solve for each resistor. Okay. Simply I'm solving for all resistor and combining that. Okay. I just want to understand the problem instead of going for step by step. Okay. So first of all, R equivalent is nothing but sum of all resistors. So just add all the resistors. 10 plus 20 plus 30, which will be equal to 60. Okay. R1, R2, R3, then R total, that is R equivalent is equal to, adding this will give the answer 60 ohm. Okay. So next one, we need to find the series current, right? So I is equal to, as per Ohm's law, V by R equivalent. So here we know the value of V, that is 12 volt, and R equivalent is 60. Okay, then 12 by 60, so which will be equal to 200 milliampere. Okay, just take the calculator and just divide 12 by 60 is equal to 0.2. So it can be written as 200 milliampere. So since all resistors are connected in series, the current through all resistors will be same. That's why they have mentioned as I1 is equal to 200 milli, I2, I3, and I total. Everything is a 200 milliampere. Okay. So next one is we have to measure the voltage across each resistor. Okay, V1, V2, V3. So V1 is nothing but I into, that is total current into R1. Okay. So for V2, I into R2, V3, I into R3. So we know the value of R1, that is 10. I is nothing but 200 milliampere. Just multiply these two. Okay. So 10 into 200, 2000. 2000 into 10 power minus 3, which is equal to 2 volt. So 2 volt for V1 and 20 into 200, that is 4000. 4 volt for V2. Similarly, 6 volt for V3. So 246. If you add all voltage up, which will give the total voltage 12 volt. So as per Kirchhoff voltage law, so 12 minus 2 minus 4 minus 6, which will be equal to 0. Now you know the value of current and voltage of each resistor, right? Now we can easily find the power. So power is nothing but P is equal to V into I. So 2 into 200 milliampere, that is 400 milliwatt. Okay. So instead of 400 milliwatt, they have mentioned as 0.4. Similarly, 200 into 4, 800, 0.8 watt. Similarly here, 1.2 watt, and finally adding all will give the total power, that is 2.4 watt. Okay. So next one we can go for resistors in parallel. Okay. So similarly, like last one, so consider two circuits, two resistors connected in parallel like this. So here I1 is the current through resistor 1 and I2 is the current through the resistor 2, and small I is the total current supplied by the voltage source, and V is the voltage across your input. Okay, that will be same for R1 and R2. That is, voltage drop across R1 is equal to V, and voltage drop across R2 is equal to V. So now our aim is to apply Kirchhoff's current law. Okay, in series we applied Kirchhoff's voltage law. Here we are going to apply Kirchhoff's current law at node A. So if you apply Kirchhoff's current law at node A, so the incoming current is equal to outgoing current. Here the incoming current is small I and outgoing current is I1 and I2. Okay, so then the formula will be I is equal to I1 plus I2. So before that, as per Ohm's law, you can measure you can just derive the value of I1. So as per Ohm's law, I is equal to V by R. Here the total voltage across R1 is V. So simply I1 is equal to V by R1 and I2 is equal to V by R2. Now apply the Kirchhoff's current law, which will be equal to I is equal to I1 plus I2. You know the value of I1 and I2. Just substitute the same here. Okay. So I is equal to V by R1 plus V by R2. Take V as a common, so which will be equal to V into 1 by R1 plus 1 by R2 is equal to 0. So as per Ohm's law, so I is equal to V by R, right? So we have taken 1 by R equivalent. So here, so instead of V by R, so instead of R we have taken R equivalent. That is, R equivalent is nothing but 1 by R1 plus 1 by R2 in numerator. Okay, that is 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So here I want to just confirm the same. Okay, so I is equal to V by R. Okay, so for that R should be in denominator. So for that we have taken this term to denominator. That's why R equivalent is written as 1 by R equivalent. 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So just to compare the same as a mathematical function. So VV get cancelled. 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Here if you take the LCM, so which will be equal to R1 plus R2 divided by R1 R2. If you take the bring the R equivalent to numerator, then it will be equal to R1 R2 divided by R1 plus R2. So this is the equivalent resistance of R1 and R2 if connected in parallel. For a two resistors connected in parallel, the equivalent circuit will be the product of two resistors divided by the sum of the two resistors. Okay, so if n number of resistors are connected in parallel, then R equivalent, that is 1 by R equivalent, is equal to 1 by R1, 1 by R2, that's 1 by Rn. Okay. Now, like what we did in resistance in series, here we know the value of I1 and I2. Okay, I1 is nothing but V by R1, and similarly I2 is nothing but V by R2. Okay, so which can be written like this. So V is equal to IR as per your Ohm's law. R equivalent we already found, right? So R1 into R2 divided by R1 plus R2. So here instead of V, just substitute this term. Okay, so I1 is equal to I into R1 R2 divided by R1 plus R2 divided by R1. So R1 will cancel, then I1 will become R2 into I divided by R1 plus R2. Similarly, I2 is equal to I into R1 divided by R1 plus R2. So this will be useful in a rule called current division rule, which will be learned in unit 2. Okay. As of now, you just learn how to find the current through resistor 1 and resistor 2 if you know the value of total current and resistor alone. So this will be the formula for that. So these are the different connection or possible connection for parallel connection. Okay. So here you can say this is, if you saw in a naked eye, simply you can say this is not in parallel because starting node are same but ending node is different. So here it is connected here, but here it is connected to this point. But if you see detailedly, so this is a short circuit. Short circuit means this point is connected here only. Okay, then the starting point and ending point both are same. Then A and B are in parallel. So here simply you can say, so starting node and ending node both are same for all 4 resistors, and here also the same, and here also the same. So here they have given us a single point, but here they have differentiated with 3 points, but these are in short circuit, hence we can consider this as a same node. That's why it's in parallel. And this is a point, this is somewhat confusing, right? So here you need to see the starting point of each resistor. Let us say A, which is connected here, similarly B is connected here and C is connected here, okay? So but this point is short circuited, so A, B, C all are connected to a single node, okay? Similarly, see the ending point of A, B, C. So A is ended at here and B is ended at here, and similarly C is ended at here, but here it is a short circuit, so ended at same node. So A, B, C are in parallel. So example, just three resistors are connected in parallel. Find the R equivalent. So R equivalent is nothing but 1 by RT is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Just substitute the values of R1, R2, R3 here and find the value. So it should be equal to 0.017. So this is not the answer. So this is the value of 1 by RT, but our aim was to find RT. So just take the reciprocal, so which will give the answer. So 85.67 is the answer. If you compare the R equivalent of parallel circuit and series circuit, simply you can see. So in parallel circuit, the overall resistance is getting decreased. See, here 200, 470, 200, but the R equivalent is 85.67. In case of series, if you connect three resistors of 100 ohm in series, total resistances become 300. So it is getting increased. Series connection resistance value will get increased, and for parallel connection resistance value get decreased. So this will be just connected to Ohm's law and infer in which connection current will be more and current will be less, whether it is for in series or parallel. So take that as your knowledge of assignment. Okay. So next one, two resistors connected in parallel and you have to find the total current and R equivalent. Okay. So which is nothing but 1 by R1 plus 1 by R2. 1 by R equivalent is equal to 1 by plus R2, or simply you can make use of the formula R1 R2 divided by R1 plus R2. Here we have directly used the formula R1 R2 divided by R1 plus R2. So which is nothing but 14,985 ohm, rounded off to 15 kilo ohm. There is no need to round off. If you want, you simply put 14.985 kilo ohm. So next sum, calculate the individual branch currents and total current from the power supply in the given circuit. So individual branch current is nothing but I1, I2, I3 and I4. So total current drawn is nothing but your IT. Okay. So here we know the value of R1, R2, R3, R4. So here see the total resistance will be less than 40, or simply you can say it will be less than 20, or even can be less than 10 also. Just measure the value. So 1 by, so there is no need to measure the R equivalent now. As of now, they have asked for individual branch current, so they didn't ask for the R equivalent. So first we will find the branch currents. Okay. So I1 is nothing but Vs, that is total voltage drop across R1, R2, R3, R4. So that is Vs by R1, that is 24 by 10, which is equal to 2.4 amps. Similarly for this R2, 24 by 20, that is 1.2 amps. For R3, 24 by 30, that is equal to 0.8, and for R4, 24 by 40, that is 0.6 amps. This is the value of each individual branch current I1, I2, I3, I4. And now we have to find the total current drawn. So for that, you can simply apply Kirchhoff's current law, because as per Kirchhoff's current law, these are the short circuit. Okay, so IT is equal to I1, I2, I3 and I4. Sum of I1, I2, I3, I4. So IT is equal to I1 plus I2 plus I4. So which will be equal to 5 amps. So this is a one way of doing or finding the total current. You can simply, or you can, if you want, you can find the R equivalent. From R equivalent also you can find the total current IT. That is IT is equal to V by R equivalent. So for that you have to first find the R equivalent. This 1 by RT is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So which is equal to this one. So if you find the value, RT will be equal to 4.8 ohm. So IT is nothing but V by S divided by RT, that is 24 divided by 4.8, which will be equal to 5 amps. Okay. So either you can simply apply the Kirchhoff's current law to find the total, or you can go for this one. Okay, that's of your choice. So additional points. So if n resistor of same value, okay, are connected in series, then the final value will be equal to n into R. Okay, simply consider this resistor. So let us say example, if I am connecting three resistors of value R as series, so R plus R plus R, which will be equal to 3 into R. So in case of 5 resistance, it will be R plus R plus R plus R, that will be equal to 5R. So in case of n resistor, same value of R, then it will be equal to n into R. Okay. So instead of going for adding, we can just multiply by the number. So if this is the case, then voltage drop across each resistor will be equal. That is, the voltage drop across this resistor and this resistor will be equal. That is equal to V by N. V is the total voltage of the circuit. N is the number of resistors. There is a 10 volt and 5 resistor. Then each resistor will share 2 volt. That is 10 by 5. That is equal to 2. Similarly for parallel connection, if there is a n resistor connected in parallel, let us say 3 resistors of same values R, 1 by R plus 1 by R plus 1 by R, which will be equal to 3 by R. That is 1 by R equivalent is equal to 3 by R. R equivalent will be R by 3. Similarly for 5, it will be R by 5. 10 R by 10. For n resistor, it will be equal to R by n. So if 5 resistor of value 10 ohm was connected in parallel, then the final answer will be 10 by 5, which will be equal to 2. Instead of going for a formula, just to make use of this simple trick, that is R by n. So in that situation, current shared by each resistor will be same, that is I by n, where I is the total current and n is the total number of resistors. So I want to continue this example. Already this takes 25 minutes of time. So I will upload these examples in a separate video. Just go to the another link that was added in the Moodle classroom for the workout example. So the workout example has some 4 problems which are all from medium to hard level. So not a simple one as we saw in the previous slides. Okay. So just to click the next link given in our Moodle classroom and watch the solved problems in our next video. Thank you guys.